Hi, today I want to speak about the newly released array data type in QuestDB. Before I dive in how to work with arrays and what's possible, I want to tell you a little bit of context why we are releasing this new data type. Arrays are especially relevant when you have data which is closely related in a table. For example, when working with market data, with financial data, it's very common to store together for each timestamp the bid price and the bid size, or the ask price and the ask size. And very often you want to take a snapshot of the market and you want to have the different prices and sizes for the bid and the ask. So what is the minimum and maximum price I want to buy an instrument for, or what is the minimum and maximum price I want to accept when I'm selling, and I want to keep this at multiple levels. For example, if I'm buying a higher amount, I expect a lower price. And in the same way, if I'm selling a small amount, I'm going to give you a higher price. So those are the price levels in the market. And it's very common to store different prices, different sizes at different moments, different timestamps in time. Those will be the market snapshots. A strategy to store this without arrays could be the one I have here on the screen. I could be storing the timestamp and the symbol, and which is the level, at the first level, second level, third level. You can have as many levels as you want. And then we are storing the bid price, the bid size, the ask price, and the ask size at that level, at that timestamp for that symbol. That means your queries with this strategy will need to group all the time by symbol and by timestamp, so the queries could get very cumbersome. So a different strategy could be storing the data in a flattened format. Imagine you want to store 20 different levels. Something you could do would be, I want to store the timestamp and the symbol. I don't need to have any label here because I'm storing the 20 bid prices and 20 bid sizes and 20 ask prices and 20 ask sizes as a single row. And this will make storing data a bit more efficient because you don't need to replicate the timestamp and the symbol every time on the storage, one per row. And when you run a query, you don't have to group by timestamp and symbol because the data is already stored by timestamp and symbol. But this doesn't give you a lot of flexibility. First, the queries are going to be a monster, as you can imagine. You have right now 82 columns in one table, so queries are going to start to look ugly. And then what happens if I have different instruments or I'm getting data from different exchanges and some of them have a different number of levels? Maybe in some of them I have only 10 levels, in other I have 250. With this strategy of storing for each level and price and size a different column, my schema is very rigid. So the two strategies we have without arrays to work with data which is closely related are not ideal. You can work with them, and in QuestDB you've been able to work with them and be very performant still without arrays. But with arrays, we are trying to tackle this problem. We are going to solve how to work with data which is very closely related and you want to store and query in an efficient way. So with arrays, you can create this. You can create this type of table. And I'll tell you in a second what an array means, for those of you that are not familiar with the term. But in an array, I'm going to do this. I'm saying, I'm going to store in one column the timestamp, in another column my symbol, in another column, I'm going to store all the bids information, and in another column, I'm going to store all the ask information. And in the bids, I want to store the price and the volume. So as you see here, I'm going to be storing two positions or two dimensions on the array, and the same for the ask. So if you're already familiar with arrays because you are a developer or you have a development background, you will know that an array is the list of data of the same type and you access the data by position, by index. So in QuestDB, an array means a list of double values, and you can access the double values by index starting by 1. In this case, I'm going to be storing in the first dimension, in the first position, I want to store the prices. In the second dimension, in the second position, I'm going to be storing the sizes. So when I access bits bracket 1, I mean the prices in this case. Bits bracket 2, it means the volumes, the sizes. Bits bracket 1 means the first price, the first level of the bits. So first thing first, here I can do this. I can select the timestamp, I can select the symbol, I can select the price at the level 1. So bits 1 is the price and bits 1 is the first price in the price array. And here I'm going to show the second level of the data. And this is what I have here. Actually, if I add the bits 1 object itself, you will see here on the bits I have the data for my 40 prices I'm storing here for the 40 levels, and then I'm accessing the first and the second level using the brackets here. Or the cool thing about arrays in QuestDB is that we don't support only accessing, of course, data individually, but we have some built-in array functions. So you can do things like counting how many elements I have. For example, here I'm checking the sizes of the volumes of the bits. So I'm counting for each element on my database, which here I have about 500 million records for the demo. So here I'm saying how many levels I have for the volumes. I can also do the sum of all the volumes. So this will be the how much liquidity I have available for the bits, for example. But I can also do things like the cumulative sum. So here, for each position, I'm getting the cumulative sum. Another cool thing about arrays in QuestDB is that we have designed them to be very efficient for storing the data in memory and disk, and also for querying the data. Instead of going with the common strategies that other databases use for storing arrays, which mimic how you store rows in many cases, we've developed arrays mimicking what data science tools like NumPy or Python do with arrays. So basically what we've done is store arrays in consecutive chunks of memory or disk storage, in which all the data for all the dimensions on the array is stored continuously as a single block. So accessing and working with the data is very fast. Since typically when you store data in an array, it's because data is very related. For example, in this case, I have one array for the bits with both the size and the price, and an array with the ask with both the size and the price, because in the common scenario, you want to work with the sizes and the prices together pretty much all the time. Accessing the data and working with that data in QuestDB is very, very, very efficient. So that's a good thing. And of course, this can be used for other type of data, not only for finance data. I'm going to be doing my demo with finance data because that's the most common use case we've found so far. But you could use arrays in other scenarios. Imagine you are monitoring some infrastructure and you have a machine with 16 CPUs and you want to store the usage and the temperature for each of the CPUs. You could use a normalized table without arrays in which you have the timestamps and the instance. You are monitoring and which is the number of the CPU, 1 to 16, which is the usage and the temperature value. But then you will have the same issues we already saw before. You are storing for the same timestamp and instance, you are storing 16 different rows. So you are storing a lot of data and you need to introduce the integer column, which is artificial. You don't really need it if you always have 16 in this case. So you could go to a next scenario in which you instead create a flattened table in which you have the timestamp, the instance, and then 16 values for the usage and 16 for the temperature, but again, the queries are going to start to look weird. So with arrays, you could just go with a solution in which you create the timestamp, the instance, the usage as a one-dimensional array, and the temperature as a one-dimensional array. So usage brackets 1 will be the first position, usage brackets 2 will be the second position, and so forth and so on, until usage or temperature bracket 16. That's about it. So you can use arrays for many different scenarios. Before I go into how you work with arrays in more detail, I want to show you first how to ingest data into arrays. And this is the easiest way of working with arrays. In my case, I'm using the Python client, but we also have the other clients also accept data in arrays with the revamped or ILP ingestion protocol to support arrays. You can also insert arrays if you are using insert statements with the Postgres protocol or with the REST API. But yeah, for ingesting data at speed, ILP and the official clients is the way to go. So the only difference is rather than sending an individual value, you need to send an array value. You need to check the documentation of the client you are using, because on Python, this is sent as a pandas array, an AMP array actually, on a data frame. But in different languages, we have different strategies. Bottom line is you use the client as you were doing until now, and you only need to take into account you have to pass an array in the shape QuestDB is going to expect it. Everything else is exactly the same, and you need to be using QuestDB 9 or higher in order to have array support. So first thing first, I have a market data table, a demo table. I ingested a few days of data here. I have only about 500 million rows, and I'm tracking 30 different price changes. So I'm representing FX, and what I have here is snapshots of the different currency pairs with the bits and the asks in the shape that I show you. The bits first dimension will be the prices, bits second dimension will be the sizes, and the same thing goes for the ask. So this is what it looks like. I have only 4 columns, and then I can access data individually. Remember, in QuestDB, we are indexing arrays starting in 1. In many programming languages, arrays start by 0, but the convention in SQL is to start indexing by 1. So we are, the first position will be 1 in QuestDB array. So bits 1 will be the bit prices, bit 2 will be the bit volumes. So if I run this, you can see here the prices and the volumes for the last 5 rows with the symbol EUR/USD. I can also ask some metadata if you want about the array. I can ask how many dimensions I have on the bits. I already told you we define 2 dimensions, so we have 2 positions we can ask. So dim length will give me how many dimensions I have. Then I can ask in the bits array in general, considering all the dimensions, how many entries do I have? And in the bits array, when you consider both the sizes and the prices, we have 80 entries per row. But in my case, I can also ask how many entries I have on the first dimension, which is the prices, how many on the second dimension, which is the sizes. And in this case, I can see I have 2 dimensions on the array. I have 80 entries, of which 40 are in the first position and 40 are in the second position. So 40 prices, 40 sizes, it all checks out. This is because of the way I've been ingesting data. I decided I was going to store prices in the first position, sizes in the second. I decided I was going to be sending for each row exactly 40 labels. These numbers could be different, but as you can see, the idea is you can apply different array functions to interrogate about the shape of the array, and how many elements you have, and so on and so forth. So I told you, the first position is the prices. So something I can do, if I want to get the best bid and the best ask price, I can go to the first position, which will be the prices, and then the first price in that second array. And the same thing for the bids. So here, when I access ask 11 and bids 11, I'm getting the best ask price and the best bid price in this array. Okay? And since I have this data, I can actually do some operations. I can get the spread. The spread means the difference between the best asking price and the best bidding price. So in this case, I can just do, since I can get the 1-1 on the ask for the best ask price and 1-1 in the bids on the best ask price, I can just subtract one from the other and I'm getting the spread. Here I'm using the column alias, but of course I could also do directly, I could just access the arrays directly by index. I could do this. I can just say, give me the first position in the prices for the ask, first position in the prices for the bids, and again, I have exactly the same information. So basically here, I'm getting the spread I have on my data, at any particular moment. The other thing you can do with arrays is to get a slice. I show you that in my arrays, I'm ingesting 40 positions right now, 40 labels for each price and size, and for each side, for the ask and for the bids. But in some cases, I might be interested only in the top 3 labels for whichever reason. So I can slice my arrays. To slice an array, you use this syntax. You use here a colon, and you have to define which is the starting position, which is inclusive, and which is the finishing position, which is exclusive. So in this case, I'm going to be getting the first 2 positions, the first 2 labels for the bid prices, and the first 2 labels for the ask prices. You can see here, this is the bid price array with 40 labels, and here I'm getting from position 1 inclusive to 3 exclusive, so I'm getting the first 2 positions for the bids and the first 2 positions for the ask. If you want the last positions, since we have here 40 elements, I will have to start in position 39 and up to 41, which wouldn't be included. So this will be the latest 2 prices. Or if I go off limits, if I try to select, for example, from position 41 to 42, you will see empty values because I don't have anything. If I start at position 40 and go up to position 42, you never get an error. What you get is just the positions for which you have values. So just the latest position, because in this case I have only 40 labels for each array. Does it make sense so far? I hope so. So the queen of the queries in QuestDB, the one I see again and again and again and again, is sampling data by time intervals. And on finance, that means totally getting candle bars, like open, high, low, and close charts. So what I can do here, I can get the, bids 1 is the prices. So if I access the first position of the prices, and then I get the first element here, I'm getting the first best price for this table. Then I'm getting the max best price for this table, the minimum best price for this table, the latest bid price for this table, and the total volume. I'm accessing now the second position. So the volume at the top level on this table, I'm doing this at 1 minute intervals. So this basically is giving me the OTLC taking into consideration only the first level of the array, which very often is what you want to get. You want to get the best price. You could play with positions, with aggregations, finding averages, whatever you need. But this is just for you to get the idea. So finding the bars with data in an array is as simple as accessing the first position of the array and then just doing aggregations as you would expect. Arrays support everything. You can run group by, sample by, word conditions, joins, window functions, anything supported for a regular column in QuestDB is supported for an array. Liquidity could be another interesting thing to query when you are storing financial data. And liquidity basically means I have different volumes, different sizes for the bids, and I have different sizes for the ask. At any given moment in time, if I'm trading in a market, I will see how much volume is available at every price level. So maybe I want to have, I can see the available volume for each instrument at every price level, but I want to get the total available volume. So what I can do is just ask, if I sum all the volumes, bids to remember is the volumes. So if I sum all the volumes for the bids and all the volumes for the ask, then I have the bid liquidity and the ask liquidity. And then if I add both of them together, I have the total liquidity. So if you want to just query liquidity or anything like that, you can just use the built-in array sum function and you are good to go. We also have functions to transpose an array and change the columns by rows. We have functions to do the dot product. If you need to do also matrix multiplication for whichever reason, I'll show you later an example of the dot product in action. We have also, you can flatten an array if you have multiple dimensions and you want to serialize into a single dimension. So plenty of functions you can use to work with arrays. When it comes to liquidity, another thing you might want to do is you might want to calculate based on the available liquidity some operations. For example, here, I want to get how much volume, how much liquidity if you want, it's available if I want to pay as much as 1% of the best available price. So I take the best available price. I don't want to pay more than 1% of that target price. How can I calculate this? By the way, this query, I have it in two versions. One is the raw SQL, and the other is the SQL using declare to make things easier to follow. But these two queries that I'm going to execute right now for you to see, they do exactly the same. And yeah, they execute in about the same time, around 15 milliseconds each when you execute, because they do exactly the same. But I want to go in the first one because it's easier to follow. So in ask1, we have the prices. So I'm going to declare prices as ask1. The volumes for the ask are stored in ask2. So I'm storing volumes as ask2. The best price is the position 1 in the prices array. So I'm going to store the best price as this. So basically the best price is the first price in the first position of the ask array. I'm going to calculate the target price, which is the best price multiplied by 1.01, because I want to stay in 1% of the best price. If I wanted to be in 50%, it will be 1.5, up to 100%, it will be 2 the multiplier. In this case, I want to stay within 1%. So I multiply the best available price times 1.01, and I can use this very convenient function, which if I have an array which is sorted, insertion point is going to give me in which position of this array I can find this value or higher. So basically here it's going to tell me, I want you to iterate over the prices array in order, and I'm going to find in which position I will meet the target price. So this is going to tell me, give me the best position for the target price. So it will tell me maybe, hey, the price you found, it's available at the level 3 or the level 4. What I'm with this, now that I'm going through the prices array, I'm going to slice the volumes array using the slicing, starting in the first position and finishing at the position we found for the price. So basically it's going to find me all the volumes for which it will be true that I can stay in the price within 1% of the best price available. And when I have this, I can do an array sum of all the volumes. So it's going to tell me within the 1% of the best price, I have these labels for the volumes, and now we are adding the total amount of those, the liquidity, if you want, for those labels, and that will give me what is the volume available that I can buy if I don't want to go over the 1% price, which is quite cool. You wanted to do this without arrays, you can do it, it's just trickier. So once you get your head around the new array functions, they are very, very, very convenient, and as you can see, they are quite efficient. Last thing I wanted to show you, last query I want to show you, because otherwise it's going to be too long, is working with market depth. So far, I've been showing you just slicing and summing the whole array and so on. But something you want to do sometimes when you want to get the depth of the market is accumulating the values from one level to the next. Because if you have, imagine you want to buy at some price level, you are able to buy at that level and to all the levels that have like a more convenient price or less convenient price, depending if you are seeing it from the bid or the ask side. But basically, very often you want to analyze the market as the cumulative volumes for the different levels. So this query helps me analyze the market depth at the different, with the different volumes, which is the available amount. What I'm doing here first, I'm just getting the first 10 rows, the latest 10 rows for year USD. And with those, what I'm doing is I'm getting the timestamp, I'm getting all the prices, I'm getting all the volumes, I'm getting the cumulative sum for all the volumes, and then I'm getting the same for the ask. So for the bids and the ask. So what this query gives me is this. It's like the prices at the first level is 1088. And these are the volumes. And these are the cumulative volumes. So what this tells me is at the second price level, which is 10879 here, the cumulative available volume is almost 200,000. For the third level in the market, for the third price level, this is the cumulative volume, as we saw in the latest query. Once you have this, you can actually represent a chart like this one. This chart is representing the cumulative volume, as you can see, is growing at different price levels. So as price is getting lower, I'm getting higher cumulative volume on the bid side. As high is getting higher, I'm getting more cumulative volume on the ask side. The last thing I want to show you with arrays, which I believe is cool, is completely different from financial data, but just for you to see the kind of doors that arrays open in QuestDB. I'm going to talk about machine learning and similarity of vectors. You might have heard in the past few years there's been a boom of AI, of course, and vector databases. Vector databases are used to store vectors that represents different dimensions of the data that are learned by machine learning models, and then you can use vectors to compare different objects, different rows in the data set between them. If two rows have very similar vectors, it means they can be closely related. That's the idea. So QuestDB is not by far a vector database. I'm not saying we're a vector database, but since now we support arrays and vectors means the same thing. A vector basically is just an array of one dimension with many values. Since now we have array support or vector support in QuestDB, you can do some basic operations for machine learning or for AI directly on QuestDB. So I went to a public dataset of word embeddings. Word embeddings means taking different words from a corpus of data and converting each word to a large vector of data. And that vector represents the word in the object space of the model. Once you have the embeddings, the vectors for each word, you can apply the dot product, mathematical dot product between two vectors. If two vectors or two arrays have a dot product which is higher, it means they are more closely related than two vectors that have a dot product which is lower. That's basically it. So in QuestDB, what I did, I created a table for word embeddings and just storing the word. Since we're a time series database, the timestamp, but in this example, I have only one timestamp per word. So I created a timestamp, I created a word, and I'm creating the embeddings as an array of doubles. I ingested the data into my table, and I have this. I have selected this from word embeddings. And for each of the 400,000 words, I have an array, which is actually quite large. I can, by the way, do something like array count embedding. And as you can see here, each vector has 100 embeddings. The embeddings don't mean anything for a human. It's just how the model, which was trained on this data, represented the data internally. But something we can do now, I can, for example, find a word. In my case, I'm using this latest on timestamp in case I have multiple entries for this word in time, which will be common on a time series database. In this case, I have only one. But I get the word queen, and I'm going to do the dot product with, I'm doing a cross join with the same table. So I'm doing the dot product between the word queen and all the other embeddings on the database. And I'm sorting, I'm comparing now with 400,000 different rows. I'm sorting this by descending order. So as you can see here, the most similar, oh, by the way, I had this query wrong. So now yes. So the most similar word to queen, which is not queen, is princess. Then the most similar after that is king, royal, her, lady, daughter, prince, Elizabeth, consort. So in this data set, as you can see, all the words at the top, they sound quite like queen. If I order ascendant, it will be the words that are less related to queen. It will be random words because, but yeah, the words less related to queen is like, I don't know, whichever is on this data set. But yeah, this doesn't sound at all like queen as we will expect. So yeah, embeddings are working here. I can do it with a word more related to, financial data like trading. So which words in this data set are most similar to trading? It's like, oh, stocks, stock, futures, exchange, shares, market, index, yen, dollar, price and cents. That sounds pretty cool to me. So something I want to experiment with is to create embeddings, for example, from OHLC bars and see with the dot product, I can actually get similarities. If I get to do that right, I'll record a video about that. But that's basically what I wanted to show you. Or I can actually do a cross join between the first 10 words and all the other words on the dataset. And in this case, I'm crossing all the words and it's telling me the most similar word to this one, to you is I, to we is I, to percent is million, to his is her. So it's telling me the most similar words for each of the words of the first 100 words on the dataset. And again, I'm doing just with arrays, doing mathematical operations. So I hope this was interesting. I hope you understand why we are very excited about arrays in QuestDB. And I would love for you to tell us how you are going to be using arrays, either here in the YouTube comments or directly on our Slack or community channels. Have a good day.